the spring of 1945. An American intelligence officer stood inside a dimly lit hangar at Lechfeld Airfield, his breath visible in the cold morning air. Before him rested the most feared aircraft of the war, the Messerschmitt Me 262. Its sleek fuselage gleamed under the weak light, twin-engine nacelles hanging beneath swept wings that seemed to belong to another era entirely. This machine had terrorized Allied bomber formations, appearing out of nowhere at speeds no propeller-driven fighter could match, then vanishing before gunners could track it. Now it sat motionless, captured, waiting to reveal its secrets. But what American engineers would discover inside those revolutionary jet engines would shock them more than any combat report ever had. The future of aviation came with a fatal flaw. If you find this story compelling, make sure to subscribe to the channel and comment where you are watching from. This is a tale of engineering brilliance, desperate compromise, and the periodic table itself conspiring against the Third Reich's last great hope for air superiority. The story of the Me 262 begins not in the desperate final months of the war, but years earlier in the summer of 1939. Before the first shots were fired, before the Blitzkrieg swept across Poland, engineers at Messerschmitt's Augsburg facility were already sketching designs for a twin-engine jet-powered fighter. The concept was revolutionary. While every air force in the world relied on piston engines turning propellers, German designers envisioned something radically different. A smooth, shark-like fuselage propelled by pure thrust, capable of speeds that would make contemporary fighters seem like relics of a previous century. The airframe took shape quickly. Willy Messerschmitt's team understood aerodynamics with an almost intuitive precision. They designed swept wings, not because wind tunnel tests demanded it, but because the wing roots needed to accommodate the center of gravity after the heavy jet engines were mounted. This accidental innovation would become standard for jet aircraft worldwide in the decades to come. The fuselage was elegant, purposeful, every curve designed to slip through the air with minimal resistance. 4 30mm cannons, packed into the nose, would give the aircraft devastating firepower against the heavy bombers everyone knew would eventually darken German skies. But the airframe was the easy part. The real challenge lay in the engines that would bring this revolutionary fighter to life. In late 1939, the Reich Air Ministry established a small development program at Junkers Motorenwerk in Dessau. A team drawn from the company's supercharger division received the impossible task of creating a reliable turbojet engine from scratch. Leading this effort was a methodical Austrian engineer named Anselm Franz. Born with the century, Franz had spent years studying the relationship between airflow, combustion, and mechanical stress. Now he would attempt to harness these forces in a way no one had ever done successfully before. Franz made a critical early decision that would define his engine's character. Unlike the Heinkel designs that used a centrifugal compressor, essentially a spinning disc that threw air outward and then redirected it backward, Franz chose an axial compressor. Picture a series of fans stacked together, each stage compressing the air slightly more before passing it to the next. This arrangement offered a crucial advantage. The engine could be much narrower, creating less drag when mounted beneath an aircraft's wing. It was an elegant solution to a complex engineering problem, but axial compressors brought their own difficulties. The interaction between spinning blades and stationary vanes created vibration patterns that could tear an engine apart in seconds if not properly controlled. Through 1940 and 41, Franz's team worked methodically through problem after problem. The compression ratio remained deliberately low, just over 3-to-1, because pushing harder would require materials and manufacturing precision that German industry could not reliably deliver. Instead of a single annular combustion chamber, they used 6 individual flame cans, a more conservative approach that sacrificed some efficiency for easier maintenance and more predictable behavior. Every design choice reflected a careful balance between ambition and practicality. Franz understood something that would later prove prophetic. The most advanced engine in the world was worthless if factories could not build it and mechanics could not maintain it. By August of 1941, the prototype engine developed 5,900 newtons of thrust, enough to demonstrate the concept's viability. That December, it passed a 10-hour endurance test at nearly double that output. The Jumo 004 was becoming real, but already the first signs of trouble were emerging from sources far beyond the engineering laboratory. The Allied naval blockade had begun strangling Germany's access to strategic materials almost from the war's first day. While Hitler's armies swept across Europe, the Royal Navy methodically cut the sea lanes that connected German industry to the wider world. Certain materials proved impossible to replace: nickel deposits in Canada, chromium from Turkey and the Balkans, cobalt from the Belgian Congo, molybdenum from scattered sources across the globe. These exotic metals were not luxuries. They were essential alloying elements that gave steel the ability to maintain its strength at extreme temperatures. Without them, German metallurgists faced an impossible choice: build engines that could not withstand jet combustion temperatures, or do not build jet engines at all. Franz and his team watched with growing alarm as the material situation deteriorated. The initial prototype engines, designated 004A, used the best alloys German industry could produce. Turbine blades made from nickel-chromium superalloys held their shape under the brutal combination of heat and centrifugal force. These early engines achieved service lives of 150 hours or more. Not exceptional by peacetime standards, but acceptable for a revolutionary technology still in development. The problem was that Germany could not produce these alloys in anything approaching the quantities needed for mass production. The Reich Air Ministry's demands were relentless. Fighter Command needed jets, hundreds of them, thousands if possible, to turn back the growing tide of Allied bombers devastating German cities. Every month that passed without operational Me-262s meant more factories destroyed, more oil refineries burning, more civilians dying in their cellars. The pressure to accelerate production became overwhelming. In response, Franz's team developed a redesigned engine, the 004B, specifically engineered for mass production with substitute materials. The changes were extensive and troubling. Where the original turbine blades used nickel-based superalloys, the production version substituted chromadur, an iron-based alloy with far inferior high-temperature properties. To compensate, engineers applied a thin aluminum spray coating to protect the steel from direct exposure to combustion gases. Hollow blade designs allowed cooling air to flow through, carrying away some of the murderous heat. These were clever solutions, innovative even, but they were also desperate compromises. Franz knew that the 004B would never match its predecessor's durability. He accepted this trade-off because the alternative was no jet engines at all. The production engines began leaving Junkers factories in early 1944. Almost immediately, reports of catastrophic failures began filtering back from operational units. Engines that had run flawlessly on test stands disintegrated after a handful of flight hours. Turbine blades warped, stretched, cracked, and finally shattered under loads they simply could not withstand. The failure mechanism was insidious. At operational temperatures exceeding 800 degrees Celsius, the iron-based alloy underwent a process called thermal creep. Under the constant stress of centrifugal force, the metal slowly flowed like extremely thick liquid, stretching millimeter by millimeter until the blades contacted the engine casing. The resulting friction generated additional heat, accelerating the failure until the entire turbine section tore itself apart. Maintenance crews at operational bases quickly learned to recognize the warning signs, a subtle vibration that had not been there before, a slight loss of power that indicated blades were no longer perfectly balanced, a temperature reading just slightly higher than normal. When these symptoms appeared, the engine had perhaps 2 or 3 flight hours remaining before catastrophic failure. The window for replacement was narrow, and spare engines were never plentiful enough. Aircraft that could have flown sat idle, waiting for factories to produce engines that would themselves fail within days of installation. Adolf Galland first flew an Me-262 on the 22nd of April, 1943. The legendary fighter ace, already credited with over 100 aerial victories, expected to be impressed by the jet's speed. He was not prepared for the revelation that awaited him. As the twin Umo engines spooled up and the aircraft accelerated down Lechfeld's concrete runway, Galland experienced something no propeller-driven aircraft could match. The acceleration was smooth, continuous, seemingly unlimited. Unlike piston engines that lost power as altitude increased and air grew thin, the jets maintained their thrust at heights where conventional fighters gasped and struggled. When Galland landed, his enthusiasm was boundless. He reportedly declared that flying the Me-262 felt like being pushed by angels. Galland immediately became the jet's most passionate advocate within the Luftwaffe High Command. He understood what this aircraft could mean for Germany's struggling air defense. The Allied bomber formations that crossed into Reich airspace each day flew in tight boxes, their defensive firepower concentrated against conventional fighter attacks. The box formations worked because German pilots had to make carefully planned approaches, matching speed with the bombers to bring their weapons to bear. An attacker who flew too fast would miss. One who flew too slow became an easy target for dozens of overlapping machine guns. The Me-262 changed this equation entirely. Its speed advantage was so overwhelming that bomber gunners could not track it effectively. A jet pilot could approach from any angle, fire a short, devastating burst, and be gone before defensive guns could respond. The 4 30mm cannons in the nose fired mine-shell high-explosive rounds designed specifically for this mission. A single hit from one of these thin-walled projectiles could blow a 4-foot hole in a bomber's fuselage. 2 or 3 hits would destroy any aircraft in the sky. Galland envisioned squadrons of jets slashing through bomber formations, scattering them, destroying dozens before escort fighters could react. If Germany could field enough Me-262s quickly enough, perhaps the daylight bombing campaign could be stopped entirely. But Galland's vision collided with the reality that Franz and his engineers already understood too well. The engines could not be trusted. Their service life had collapsed from 150 hours to perhaps 10 or 25, depending on how carefully the pilot managed thrust settings. A cautious flyer who avoided sudden throttle movements and kept power settings moderate might coax 50 hours from an engine. A pilot who flew aggressively, as combat demanded, might destroy his engines in a week, and replacement engines were never available in sufficient quantities. Production at Junkers factories could not keep pace with attrition. Even without enemy action, the Me-262 force was consuming itself. The operational challenges extended far beyond engine life. The Jumo 004 shared a common weakness with all early turbojet designs. Its throttle response was dangerously sluggish. A piston engine reacted almost instantly to throttle inputs, speeding up or slowing down as the pilot demanded. The jet engine required time. The compressor had to accelerate. Fuel flow had to increase proportionally. Temperatures had to stabilize at new levels. A pilot who advanced the throttle too quickly would pump excess fuel into the combustion chambers before the airflow increased to match. The result was a temperature spike that could exceed the turbine blade's already marginal heat tolerance. A single moment of carelessness, a throttle slammed forward in a moment of panic, could destroy an engine that had survived hours of careful operation. Training programs for Me-262 pilots emphasized these limitations relentlessly. New pilots learned to treat the throttle like a surgical instrument, making gradual adjustments measured in seconds rather than fractions of seconds. They learned the specific sequences for starting the engines, the precise temperatures and speeds that indicated normal operation, the warning signs that predicted imminent failure. They learned that landing approach, when throttle adjustments were frequent and margins for error narrow, was the most dangerous phase of any flight. Many Me-262s and their pilots were lost not to enemy action, but to engine failures during landing, when there was no altitude to spare for emergency procedures. Take a moment to subscribe and comment where you are watching from. The story continues with the operational nightmare that unfolded across Germany's remaining airfields. Jagdgeschwader 7 was the first true jet fighter wing established in the autumn of 1944 to defend the Reich against the endless procession of American bomber formations. On paper, the unit looked formidable. Experienced pilots, many of them veterans of years of combat, assigned to the most advanced aircraft in the world. In reality, JG-7 exemplified the Me-262's fundamental problem. Unit records from October 1944 tell the story in stark numbers. 38 aircraft assigned, typically only 12 to 15 operational on any given day. The remaining 24 sat silent, grounded by engine problems, waiting for replacements that might arrive tomorrow or next week, or not at all. The mathematics of engine life imposed a brutal operational rhythm. Each aircraft required 2 Jumo 004 engines. Each engine lasted perhaps 15 hours under combat conditions. This meant that maintaining a single Me-262 in operational status required roughly 4 engine changes per month during intensive operations. For a unit of 40 aircraft, this translated to 160 engine changes monthly just to break even. Add combat losses, training accidents, and the inevitable percentage of engines that failed prematurely, and the numbers became staggering. JG-7 needed 80 to 100 engine changes monthly to maintain its strength. Junkers factories were producing approximately 5,000 engines across the entire war, but distribution systems were breaking down under Allied bombing, and every other jet unit in Germany was competing for the same limited supply. The human cost of this mechanical crisis fell heavily on maintenance crews. These men worked around the clock in conditions that deteriorated weekly. Allied bombing had destroyed many established airfields, forcing jet units to operate from highway strips and improvised facilities. Spare parts that had once moved through organized supply chains now arrived sporadically or not at all. Mechanics improvised, cannibalized damaged aircraft, adapted tools designed for piston engines to work on jets they barely understood. The accumulated knowledge required to keep Me-262s flying existed primarily in their heads, passed from experienced technicians to newcomers through exhausting on-the-job training. Oberfeldwebel Klaus Neumann represented this generation of mechanics who knew the terrible truth about their revolutionary aircraft. Opening engine cowlings after just 9 flight hours, he found what he had come to expect. Turbine blades warped beyond recognition, their precisely machined profiles distorted by thermal creep. Hairline cracks spreading through metal that should have been pristine. Complete structural failure from what should have been routine operation. Neumann understood that every flight brought catastrophic failure closer. He understood that the world's fastest fighter spent most of its existence grounded, not because of enemy action, but because German industry could not produce the alloys needed to keep revolutionary technology functioning. The pilots understood too. Their briefings emphasized tactics designed to preserve engines as much as to defeat enemies. Approach targets from high altitude using gravity rather than thrust. Make single fast passes rather than extended engagements. Avoid afterburner use except in emergencies. Manage throttle movements during landing approach as if lives depended on it, because they did. Combat flying demanded aggressive maneuvering, rapid throttle changes, engines running at maximum output. Everything that made a fighter pilot effective also destroyed the engines that kept him flying. The contradiction was inescapable. Franz Schall was one of the pilots who mastered this impossible balance. Flying with JG-7, he developed techniques that maximized the Me-262's advantages while minimizing the stress on its fragile engines. His attack profiles emphasized the shallow diving approach that his fellow pilots considered most effective. Coming in from altitude with engines throttled back, building speed through gravity rather than thrust, he could make a single devastating pass while preserving his power plants for the next mission. On one occasion, approaching a formation of consolidated B-24 Liberators, he closed to within 200 meters before triggering his cannons. The shells struck the bomber's cockpit, apparently eliminating both pilots, and the aircraft flipped inverted and entered an uncontrollable spin. Schall knew better than to watch it go down. He was already climbing away, throttle advanced just enough to maintain separation, preserving his engines for the flight home. Not every pilot survived long enough to develop such skills. The training pipeline could not produce experienced jet pilots fast enough to replace losses. New pilots entered combat with sometimes fewer than 10 flight hours in type. They did not know the throttle techniques that preserved engines. They did not recognize the subtle vibrations that warned of imminent failure. They flew aggressively because that was what their conventional fighter training had taught them, and they destroyed their engines, and sometimes themselves, before they could learn better. The Me-262's operational limitations were self-reinforcing. Poor engine reliability meant limited training flights, which produced inexperienced pilots who flew poorly and destroyed more engines, which further limited training opportunities. By December 1944, Galland had compiled enough operational data to present a comprehensive report to Hermann Göring, commander of the Luftwaffe. The document, later recovered and translated by Allied intelligence, stated the problem explicitly. Me-262 operational availability averaged 30 to 35% due almost entirely to engine limitations. Aircraft that should have been devastating bomber formations sat idle on dispersed airfields, their engines worn out, awaiting replacements that production could not supply. Galland calculated that meaningful air defense required a minimum of 1,500 new engines monthly. Junkers was producing approximately 600. The gap was unbridgeable. Göring's response to this report remains unclear from surviving records. What is clear is that nothing changed. Production continued at the same inadequate pace. Engine life remained catastrophically short. Operational availability stayed mired in the 30% range. The most advanced fighter aircraft of the Second World War was defeated not by Allied pilots, but by the periodic table itself. The elements that could have made the Jumo 004 a reliable engine, nickel, chromium, cobalt, molybdenum, lay in deposits thousands of miles away, cut off by naval blockade and enemy occupation. German engineering ingenuity, remarkable as it was, could not substitute for atoms that were not there. The Allies watched this drama unfold with intense interest. Intelligence services compiled reports from captured pilots, crashed aircraft, and agents inside occupied Europe. The picture that emerged was simultaneously threatening and reassuring. The Me-262 was everything German propaganda claimed, a revolutionary aircraft that outclassed every Allied fighter in speed and climb rate. But it was also fragile, unreliable, and operationally constrained in ways that limited its effectiveness. American and British planners concluded that they did not need to defeat the Me-262 in aerial combat. They merely needed to survive its limited sorties, while their overwhelming industrial advantage wore down whatever remained of German air power. This strategy found expression in the systematic bombing of German transportation networks and petroleum production. Jet engines consumed prodigious quantities of fuel compared to piston engines. The Me-262 burned through its internal fuel load in roughly 90 minutes of flight time. Without adequate fuel supplies, jets could not fly regardless of engine availability. Without functioning rail networks, engines produced in Junkers factories could not reach operational units. Without electrical power, the factories themselves could not operate. Every strategic bombing raid, even those that missed their primary targets, contributed to the cumulative degradation of German industrial capacity. As the Reich contracted under Allied pressure from east and west, the Me-262's operational difficulties multiplied. Airfields were overrun or rendered unusable by bombing. Supply lines collapsed entirely. Pilots who survived combat found themselves stranded without fuel or spare engines. Some units attempted to disperse their aircraft along highway strips, hiding jets under forest canopy during daylight and emerging for quick strikes at dusk. The tactical benefits were minimal. The logistical complications were enormous. An aircraft hidden under trees still needed engines, fuel, ammunition, and trained ground crews. None of these were available in adequate quantities. The final months of the war saw desperate improvisations. Slave laborers from concentration camps were pressed into engine production, working under brutal conditions in underground factories. The quality of their work reflected their circumstances. Some deliberately sabotaged engines, placing debris in turbines or introducing flaws that would cause failures after installation. Others simply lacked the training and nutrition needed to perform precision manufacturing work. Engines that reached operational units were often defective in ways that only became apparent after installation, or worse, during flight. The Allied armies that swept across Germany in spring 1945 encountered this disintegrating jet program at every major airfield. At Lechfeld, where Galland had first flown an Me-262 2 years earlier, American forces found 15 jets in various states of disrepair. Some had been booby-trapped by retreating Germans. Others sat with open-engine cowlings, their power plants removed for installation in aircraft that no longer existed. A few were essentially intact, waiting for engines or fuel or pilots that would never arrive. The technology that could have changed the air war had been defeated by the war itself. Operation Lusty, an acronym for Luftwaffe Secret Technology, was the American effort to capture and evaluate German aeronautical achievements before they could be destroyed or fall into Soviet hands. Colonel Harold Watson led one of two primary collection teams, quickly nicknamed Watson's Whizzers, for their aggressive pursuit of high-value targets. Their mandate was comprehensive. Locate aircraft on the blacklist of priority items, render them flyable if possible, transport them to collection points for shipment to the United States. Every German aircraft type of significant technical interest was on that list, but the Me-262 sat at the very top. Watson's team arrived at Lechfeld to find chaos and opportunity in equal measure. German mechanics and test pilots, their war obviously lost, proved surprisingly cooperative. Some had been flying jets for months, accumulating expertise that no American pilot possessed. Others understood the engine systems intimately, having supervised maintenance through the desperate final months. Watson recognized that these men were as valuable as the aircraft themselves. Under circumstances that remain partially classified, some of these German personnel were recruited to assist in recovering and flying captured jets. The recovery operation required extraordinary measures. Many Me-262s could not be flown due to engine problems. These were disassembled and loaded onto trucks for transport. Others were coaxed into operational condition, using whatever parts could be scrounged from damaged aircraft. German pilots flew some jets to collection points, accepting American assurances that cooperation would be remembered favorably. The aircraft were gathered at intermediate airfields, processed, and eventually shipped to Cherbourg, where they were loaded aboard the escort carrier USS Reaper for transport across the Atlantic. The journey was not without incident. Salt air threatened to corrode sensitive aluminum components. Movement during the Atlantic crossing stressed airframes never designed for shipboard handling. At Newark Army Airfield, the captured aircraft were unloaded and transported to Wright Field in Ohio, where American engineers would finally have the opportunity to examine German jet technology in detail. Colonel Watson's evaluation team approached the Me-262 with methodical precision. Their mandate covered everything: flight characteristics, structural design, armament, instrumentation, and above all the engines that made jet flight possible. The Jumo 004 was dissected, measured, tested, and analyzed in ways that Junkers' own engineers had never attempted. What the Americans discovered confirmed intelligence reports while adding disturbing new details. The metallurgical analysis proved particularly revealing. Specialists at the National Advisory Committee for Aeronautics examined turbine blade samples under microscopes, subjected them to stress testing, and analyzed their chemical composition. The results showed exactly what Franz's team had been forced to accept years earlier. The iron-based alloy used in production engines simply could not maintain structural integrity at operational temperatures. Where Allied jet engines used nickel-based superalloys that remained strong and stable even at extreme heat, the German substitute material softened, stretched, and ultimately failed. The aluminum spray coating that protected blade surfaces degraded rapidly under combustion conditions, exposing the underlying steel to temperatures it could not withstand. American engineers identified the specific failure mechanism with clinical precision. Thermal creep, the slow deformation of metal under sustained stress at high temperature, initiated the destruction. Turbine blades stretched fractionally with each flight hour, their carefully balanced weight distribution becoming progressively more uneven. The resulting vibration stressed attachment points and adjacent components. Eventually, elongated blades contacted the engine casing, generating additional friction and heat that accelerated the final collapse. An engine might show no obvious external symptoms until minutes before catastrophic failure. The only reliable predictor was flight time, and the safe window was measured in single digits of hours. Flight testing of captured Me-262s confirmed the performance advantages that had made the aircraft so feared. American test pilots achieved speeds exceeding 830 kilometers per hour in level flight, with dive speeds approaching 950. The acceleration was smooth and seemingly effortless compared to piston-powered fighters. Handling characteristics were generally positive, though the aircraft exhibited some longitudinal instability at high Mach numbers that required careful pilot technique. The swept-wing design, adopted for center-of-gravity reasons rather than aerodynamic theory, proved well suited to high-speed flight. In many respects, the Me-262 was exactly what German propaganda had claimed, the most advanced fighter aircraft of its era. But the engines remained the fatal weakness. Test pilots learned the same throttle management techniques that German pilots had developed through bitter experience. They discovered the same narrow tolerances for temperature and vibration that separated safe operation from imminent failure. One captured Me-262 was lost on the 20th of August, 1946, when an engine caught fire during a test flight over Ohio. The pilot, Lieutenant Walter McCauley, ejected safely and survived. The aircraft crashed near Lumberton and was completely destroyed. Even under controlled test conditions with experienced pilots and careful maintenance, the Jumo 004 could not be trusted. The broader lessons of the Me-262 program were not lost on American planners. The aircraft demonstrated conclusively that jet propulsion represented the future of military aviation. Speed advantages of 100 miles per hour or more over the best piston fighters could not be ignored. The ability to maintain performance at high altitude opened tactical possibilities that propeller aircraft could not match. Every major air force would need jets, and quickly, to avoid being rendered obsolete by rivals who developed them first. But the German experience also showed what happened when revolutionary technology outpaced the industrial base needed to support it. The Me-262 was a monument to German engineering brilliance and a testament to the futility of fielding advanced weapons without the resources to sustain them. 1,400 airframes had been produced, but operational availability never exceeded 40% and usually hovered around 30%. More jets were destroyed by their own engines than by enemy action. The program consumed irreplaceable resources, skilled labor, scarce materials, factory capacity that might have produced thousands of conventional fighters with far greater aggregate combat effectiveness. American jet development took a different path. The materials blockade that had crippled German efforts never constrained Allied industry. Nickel from Canada, chromium from multiple sources, cobalt, molybdenum, tungsten, all flowed freely to American factories. General Electric and Westinghouse developed turbojet engines using superalloys that German metallurgists could only dream about. These engines lasted hundreds of hours between overhauls, not tens. The operational reliability that Franz could never achieve became routine for American designs. The Lockheed P-80 Shooting Star, America's first operational jet fighter, entered service too late to see combat in Europe. Its General Electric engines benefited directly from analysis of captured German technology, but more importantly, they benefited from access to materials that made reliability possible. Where the Me-262 required constant engine changes just to stay operational, the P-80 could fly mission after mission with routine maintenance. The revolutionary technology that Germany pioneered became practical only when combined with the industrial resources that Germany lacked. Anselm Franz himself became part of this transition. After the war, he was recruited under Operation Paperclip, the American program that brought German scientists and engineers to the United States. He joined Lycoming's turbine engine division in 1951, bringing decades of experience to American gas turbine development. The principles he had pioneered in the Jumo 004, axial compressor design, combustion chamber arrangement, turbine cooling, found expression in engines that had access to the materials his wartime designs had been denied. Franz's subsequent career included development of the T-53 turboshaft engine that powered the legendary UH-1 Huey helicopter and contributions to the first high-bypass turbofan designs. The engineering genius that had created the world's first mass-produced jet engine went on to shape American aviation for decades. The Me-262's legacy extends far beyond its wartime service. The aircraft proved concepts that every subsequent jet fighter would incorporate: swept wings, axial flow turbojet engines, high-speed aerodynamic design. All found their first practical expression in Messerschmitt's revolutionary fighter. The mistakes were as instructive as the successes. Post-war designers understood that engine reliability mattered as much as engine power. They understood that metallurgy constrained performance as surely as aerodynamics. They understood that revolutionary technology required revolutionary supporting infrastructure to deliver on its promise. Make sure to subscribe and comment where you are watching from. The conclusion of this story reveals the ultimate irony of German jet development. The men who flew and maintained the Me-262 understood its nature better than anyone. Captured German pilots told Allied interrogators that the aircraft was the finest fighter in the world when it had working engines. It rarely had working engines. This summary captured the essential tragedy of the program. Germany had created something genuinely revolutionary, a glimpse of aviation's future that arrived years ahead of schedule. But creating technology and fielding it operationally were entirely different challenges. The Me-262 demonstrated both German engineering excellence and the limits of engineering when divorced from industrial reality. The pilots who flew these aircraft into combat showed extraordinary skill and courage. They learned to manage temperamental engines through throttle discipline that required constant attention. They developed tactics that exploited their speed advantage while minimizing the engine stress that aggressive flying caused. They accepted that each mission might end with an engine failure that no skill could prevent. And they continued flying because the alternative was watching their country burn under Allied bombs without any chance of resistance. The mechanics who kept these aircraft operational deserve equal recognition. Working with inadequate tools, insufficient spare parts, and engines that failed at rates no previous aircraft had exhibited, they somehow maintained enough jets to mount a credible air defense effort. Their accumulated knowledge, passed from experienced technicians to newcomers, represented an irreplaceable institutional asset that collapsed along with the Reich itself. The expertise required to keep Me-262s flying died with the men who possessed it or dispersed when they scattered after the surrender. The engineers who designed the Jumo 004 faced choices that had no good outcomes. They could build engines with proper materials that German industry could not supply in adequate quantities, or they could build engines with substitute materials that would fail after a handful of flight hours. They chose the latter because any jet engines were better than no jet engines, and because they hoped that somehow the war would end before their compromises became critical. This hope proved unfounded. The war continued long enough for the engine's limitations to become fully apparent, but not long enough for improved designs to reach production. Franz himself knew from the beginning what the substitute materials would mean. He designed the 004B knowing its turbine blades would fail under stresses the original design could have withstood. He accepted this because his country needed jet engines, and he was the man who could provide them. The moral weight of that decision, building weapons he knew were flawed for a cause he may have questioned, remains unknowable. What survives is his engineering legacy, the principles he established that made jet aviation possible, first for Germany and then for the world. The strategic implications of the Me-262 program remain debated among historians. Some argue that earlier deployment could have changed the air war's outcome, forcing the Allies to adopt tactics that limited bombing effectiveness. Others point out that the engine problems would have appeared regardless of when production started, and that no number of unreliable jets could have stopped the combined industrial might of the United States and British Empire. What seems clear is that the program consumed resources, particularly skilled labor and factory capacity, that might have been used more effectively for conventional aircraft production. The fundamental lesson of the Me-262 is that technology alone does not win wars. Industrial capacity, material resources, trained personnel, supply chains, maintenance infrastructure, all must align to translate revolutionary designs into operational capability. Germany possessed engineers capable of creating the most advanced fighter aircraft of the 1940s. Germany did not possess the nickel deposits, chromium mines, or secure trade routes needed to build engines that worked reliably. The periodic table, not pilot skill or design brilliance, determined the outcome. When American engineers at Wright Field completed their evaluation of captured Me-262s, they produced reports that documented both the aircraft's capabilities and its limitations in exhaustive detail. These reports circulated through the Air Force technical community, influencing designs that would appear in the late 1940s and beyond. The lessons were clear. Jet propulsion was the future. Engine reliability was essential. Material science would determine what was possible. And revolutionary technology required revolutionary industrial support to become more than a fascinating prototype. The Me-262 survives today in museums around the world, preserved as a monument to one of aviation's most significant technological leaps. Visitors who see these aircraft often marvel at their sleek lines and obvious speed. What they cannot see are the turbine blades within the engine nacelles, the components that determined whether these beautiful machines flew or sat grounded. Those blades, made from the wrong materials by engineers who knew better, but had no alternative, tell the true story of the Me-262. Engineering brilliance constrained by industrial reality. Revolutionary vision limited by the elements that compose the Earth's crust. The future of aviation trapped in an engine that could not survive its own operation. The captured jets that Watson's whizzers flew to collection points, loaded onto ships, and transported across the Atlantic represented more than war trophies. They were data points in the ongoing evolution of military aviation. Every test flight, every engine teardown, every metallurgical analysis contributed to understanding that shaped subsequent designs. The Me-262's flaws were as instructive as its virtues. American engineers learned what not to do from German mistakes, learned which shortcuts led to catastrophic failures, learned that some compromises could not be sustained regardless of operational pressure. The Jumo 004's reputation as a death trap was earned through thousands of failures that stranded aircraft, ended careers, and took lives. Yet the same engine represented a genuine achievement in turbojet development. Franz and his team created a mass-producible, axial-flow turbojet engine years before anyone else accomplished the same feat. That they did so under wartime conditions, with deteriorating material supplies and relentless schedule pressure, makes the achievement more remarkable rather than less. The engine worked well enough, often enough, to put jet fighters into operational service for the first time in history. Its failures were consequences of circumstances beyond engineering control. The spring morning when American intelligence officers first entered that hangar at Lechfeld marked the end of one era and the beginning of another. The Me-262 they examined would never fly against Allied bombers again, but its descendants, refined through decades of development that incorporated its lessons, would dominate military aviation for the rest of the century. The swept wings, the jet engines, the high-speed aerodynamics all trace their lineage to Willy Messerschmitt's design team and Anselm Franz's engine laboratory. The death trap engines that limited what the Me-262 could accomplish also demonstrated what jet propulsion could eventually become. Every jet aircraft flying today carries some trace of those desperate engineers in Dessau and Augsburg, working with inadequate materials to create something unprecedented. Their success was incomplete, compromised by circumstances they could not control. But their vision proved correct. The future did belong to jet propulsion, to swept wings, to speeds that piston engines could never achieve. The Me-262, for all its flaws, showed what that future would look like. American engineers who studied captured examples understood that the German achievement, though limited by material constraints, pointed toward possibilities that their own industrial base could fully realize. The pilots and mechanics who struggled with failing engines, who watched magnificent aircraft set idle for want of spare parts, who flew missions knowing their power plants might quit at any moment, deserve to be remembered as more than footnotes in aviation history. They operated revolutionary technology under impossible conditions, extracting whatever combat value they could from machines that consumed themselves through normal operation. Their skill and dedication could not overcome the fundamental material shortage that doomed the program, but they tried. That effort, sustained through months of deteriorating circumstances, represents something admirable even in the service of an indefensible cause. The Me-262's story ultimately is not about German engineering failure. The engineering was remarkably successful given available resources. It is about the limits of engineering when confronted with material constraints that no cleverness can overcome. Nickel and chromium and cobalt are not substitutes for each other. The atomic properties that make these elements suitable for high-temperature applications cannot be replicated by iron regardless of how it is processed. Franz's team did everything possible with available materials. What was possible was not sufficient. This lesson resonates beyond military aviation. Revolutionary technology in any field depends on supporting infrastructure that may not be immediately apparent. The materials, manufacturing processes, supply chains, and trained personnel that enable advanced systems often matter more than the systems themselves. Creating something revolutionary is only the first step. Sustaining it operationally requires resources and capabilities that revolutionary designers may not control. The Me-262 demonstrated this principle with terrible clarity. When that American intelligence officer stood in the Lechfeld hangar, examining Germany's most advanced fighter aircraft, he was looking at both a remarkable achievement and a cautionary tale. The achievement was obvious: elegant airframe, revolutionary engines, performance that exceeded anything the Allies could field. The cautionary tale required deeper examination: the turbine blades that could not withstand their operating environment, the maintenance logs documenting constant failures, the grounded aircraft awaiting engines that would never arrive. Together, achievement and failure told a complete story about technology, resources, and the harsh mathematics of industrial war. The engines were indeed a death trap, killing pilots and grounding aircraft and consuming resources that Germany could not afford to waste. But they were also the first mass-produced jet engines in history, pioneers of a technology that would transform aviation forever. The death trap designation, while accurate, captures only part of the truth. These engines also represented triumph, albeit incomplete and compromised, of human ingenuity over fundamental technical challenges. That the triumph was limited by material shortages beyond engineering control does not diminish the accomplishment of creating functional jet propulsion when no one else had done so. The last Me-262 missions were flown in the final chaotic days of the war, when fuel was almost unobtainable and engine spares had stopped arriving entirely. Pilots flew until their engines failed, then walked away from aircraft that would never fly again. The revolutionary technology that could have changed the air war ended not with a dramatic final battle, but with quiet mechanical failures across a dozen dispersed airfields. The jets that survived intact enough to be captured represented a fraction of total production, most having been destroyed in combat, accidents, or deliberate sabotage during the retreat. What Watson's Whizzers shipped back to America was therefore a sampling of German achievement at its best, aircraft that had survived to be captured intact. The evaluation results reflected this selection bias somewhat. Test aircraft performed adequately because they had been adequately maintained. Operational units facing constant engine changes and parts shortages experienced the Me-262 very differently. The American reports, thorough as they were, could not fully capture what it meant to keep these aircraft flying under actual wartime conditions. The final irony of the Me-262 program is that it succeeded and failed simultaneously. It succeeded in proving that jet-powered fighters were practical, that their performance advantages were decisive, that the future belonged to turbine propulsion. It failed in delivering those advantages to Germany's air defense when they were needed. The success would shape aviation for generations. The failure contributed to Germany's defeat. Both outcomes flowed from the same source: revolutionary engines that German industry could build but could not build well enough to sustain operationally. American intelligence officers who compiled their final reports on captured German aviation technology understood that they were documenting a turning point in military history. The piston engine era was ending, killed by German engineers who could not sustain what they had created, but who had demonstrated its potential beyond any doubt. The jet age would begin properly only when other nations, with access to better materials and more stable industrial bases, could deliver on the Me-262's promise. That delivery came quickly. Within 5 years of the war's end, jet fighters dominated military aviation worldwide. Within 10 years, jet-powered airliners began replacing propeller aircraft on commercial routes. Within 20 years, jet engines powered everything from helicopters to missiles to industrial equipment. The revolution that German engineers initiated, then watched collapse under material constraints they could not overcome, transformed the world in ways they could only imagine during those desperate final months. The Me-262 remains a symbol of what might have been and what eventually became. Its sleek lines promised a future that arrived only after the war ended and the material constraints that had limited its engines disappeared. The death trap engines that American engineers examined in Ohio laboratories were both an ending and a beginning. They ended Germany's hope for air superiority and began the modern jet age that continues to this day. Both meanings are essential to understanding what the Me-262 represented and why it matters. The aircraft that once terrified Allied bomber crews now sit silently in museums, admired by visitors who know it only as a historical curiosity. The engines that stranded pilots and frustrated mechanics have been replaced by modern turbofans that deliver tens of thousands of hours between overhauls. The materials that Germany lacked flow freely through global supply chains that span continents. Everything that made the Me-262 a death trap has been solved by subsequent generations of engineers building on foundations that Franz and his colleagues established. That is perhaps the most fitting legacy for an aircraft that promised so much and delivered so little during its operational career. The Me-262 failed to save Germany from defeat. It succeeded in showing the world what aviation could become. The death trap engines were stepping stones to something better, necessary failures on the path to reliable jet propulsion. Without the Jumo 004's problems, engineers might not have understood what they needed to solve. Without its partial successes, they might not have known what was possible. When American pilots finally completed their evaluation flights of captured Me-262s, they filed reports that confirmed what combat pilots on both sides had already learned. The aircraft was magnificent when its engines worked. Its engines rarely worked reliably. This contradiction defined the Me-262's entire operational history and ensured its place as one of aviation's most significant and most tragic achievements. Revolutionary enough to change the future, flawed enough to fail in the present, the Me-262 remains forever, both symbol and warning. Engineering brilliance, when constrained by material reality, cannot overcome the fundamental chemistry of the elements. The periodic table won the battle for air superiority over Germany not through any strategic plan, but simply by being what it is. Some things cannot be engineered around.